Hello everyone. We'll start our lecture. It is a kind of a review, and those who may have heard electrodynamics or electromagnetics, and this is just a brief review for the wave part. Okay, so we are going to talk about wave motion, Maxwell's equations, and then electromagnetic wave, and then we are going to talk about energy and momentum of light. Okay. So those who have already taken the optics course, you can go back to HACT. Okay. Optics is a study of light, and especially in the wave optics or physical optics, light is an electromagnetic wave, and we are dealing with wave phenomena such as the diffraction and interference. But in the case of a geometrical optics, light is a ray, and we were thinking about how the lens is going to bend the light, such as the refractions, and those are things main concern of the geometrical optics. In quantum optics, light is particles, and we are going to talk about some cases for the lasers, and we are not going to go into very detail of the lasers, but we are assuming that laser is a quantum optic nature. Okay. So our main point is a wave optics or free optics. So we need to think about how we define the wave. A wave is a self-sustaining energy-carrying disturbance of a medium through which it propagates. There are two types. One is the longitudinal wave, and the other one is the transverse medium. Electromagnetic wave is the transverse wave. For the case of a sound wave, it's a longitudinal. When a wave propagates, the disturbance advances not the medium. The disturbance is the, for instance, in the case of a transverse wave, in a loop, you see that the loop itself is not moving, only the displacement of the rope is changing. So that is the main difference. Okay. So a mathematical expression of wave is basically if a function is given by this form, then we can say that this is a form of a wave with the propagation velocity of v. Note that x is the position, t is the time, and the v is the velocity. Okay. So here are some of our exercises. You can think about this MATLAB as an exercise and try to solve it as much as possible. It's not mandatory, just try to do it, and then I think I will give you extra points. But you don't have to solve all of them. Okay, so here is the 1-1 is use MATLAB or equivalent software for plotting. And the first thing is to make a bell-shaped wave function, and it is given by this one. And make a wave function moving minus x from the following poles. Fx is this one, and then instead of x, you just put the x minus vt, x plus vt. That means you're moving toward minus x directions. Okay, and then now you have these two functions. And then you can plot this one as a function of a time, -2, -1, etc. Okay, so you just plug in t here and then you plot them. So wave equation is the very important one. So we are going to talk about the diffractions and interference, but the starting point is the wave equations. Wave equation is given by these differential operators. The second derivative in the time, and second derivative in the space, and second derivative in time, and those two are mediated by the velocity of the wave. Okay, so it's a space-time correlations. So in other words, wave is a space-time object that is where the space and time is correlated with the propagation velocity v. Okay, so you can think about the exercise if you want to. And then if wave is in the 3 dimensions, in the case of a Laplacian or Cartesian coordinate, you can have these spatial operator, differential operators, and time domain operators. Okay, so in 3D, wave equation is given by this one. Okay. So instead of the partial derivative in 1 dimension, it is changed into the Laplacian. Okay. And especially as a solution of this wave equation, we can think about harmonic waves. Harmonic wave is given by this one, kx minus plus vt, or kx minus plus omega t. Okay, but we are going to talk about it. But important thing is that x plus minus vt is the beta basis of a wave function solutions. And then there's a k comes in. K is the actually the wave number. Okay? And then this is the wave in the 1-dimensional case. And then it's time to think about what kind of information can you get from the harmonic wave. So note that there is amplitude, there is a wave number k, and the velocity here. And then the period can be found by this one, and frequency can be found by this one. Okay, and angular frequency is given by omega is 2 pi nu here. So the same equations can be rewritten in terms of k and omega. K and omega. K is the wave number, its dimension is one of the lengths, and omega is angular frequency, and its dimension is one over time. Okay, so you can have various expressions like this, kx plus minus omega t, or in terms of lambda and the tau, or you can have a v and frequency nu, and you have a different type. Okay. So basically, from the harmonic wave, we can find out the wavelength, frequency, and the wave number. Okay, that is the important thing. Wave number, frequency, wave number, the frequency here. Where is the frequency? Okay. Okay, anyway, we can just skip. Omega is the frequency. And it's time to think about the phase. Phase is that this term. The phase is kx plus minus omega t here. And non-zero initial phase, you can add some of the initial value here. And this phase is very important information in wave. For instance, the phase velocity of a wave is defined as this one. For the constant phase, the wave front is moving. So how the constant phase is moving as a function of time is the phase velocity. And then after some calculations, you'll find out that phase velocity is nothing but omega over k. So as an extension, we can think about harmonic plane wave. harmonic plane wave is nothing but this form. In three-dimensional form, we have a now vector, k vector, and k is a wave vector. So in one-dimensional case, k was wave number, but in the case of a three-dimensional vector cases, we call k vector as a wave vector. And if you look at it, this is defining a phase, constant phase in a plane, simply because if you put the kr equal to constant, and that means the k is the normal vector of that plane. So if you use k, and k is the perpendicular to plane, okay. And other case of a harmonic wave is a spherical wave. Is given by this one. So similar phase term, but we have a amplitude over r, such that it has a spherical propagations. Okay. So what you need to know is that this is your plane wave, and this is your spherical wave. You need to distinguish them. Wavefront is the for plane wave, the wavefronts are planar surface for which k dot r is constant. For spherical wave, the wavefronts are concentric spheres centered at origin of the wave. So it's the very different things. And the electromagnetic wave has an electric field component and a magnetic component, and both of them have a same phase. Okay, note that phase term for magnetic field and electric field are the same. But of course, because of the electromagnetic wave nature, there is a correlation between E0, B0, and K. They are all orthogonal to each other. And for this electric field and magnetic field, we have a Maxwell's equation in the integral form, or differential form. Okay. So we have a J is the current and rho is the charge density. And if we have a certain medium, then medium has two components. One is the polarization, and the other one is the magnetization, P and M. Okay. So electric field in the medium has a certain polarization such that medium will feel different electric field due to polarizations. Okay. So internal electric field is different from external one, such that you have this form. Okay. And another thing is that there is if there is a lossy resistance, or J equal to sigma E, that is a current driven by this Ohm's law, and the electric field is inducing a current with the conductivity sigma, then we have another contribution of the current, not with the free current. Okay, so that we have a induced current here. So in the medium, we should think about the P, polarization, and this current. Okay, so these two are important contribution of medium to electric fields. Note that this psi and the sigma will depend on material. If you have a different material, the different materials have a different value, psi and sigma, and then you have a different polarization and different electric field, the electric current. Okay. And for the case of a magnetic field in the medium, you have a magnetization, magnetic polarization, or magnetization is called M. And then it is kind of aligning the magnetic dipole. So magnetization M is actually magnetic dipole, and polarization P is electric dipole. Okay. And one thing you need to not confuse here is that this polarization should not be confused with the light polarization. Light polarization is the direction of the electric field vector of the light. So in the case of here, the direction of the plane wave, for instance, we call it also polarization. It could be linear polarization, circular polarization, or elliptic polarization, but it has nothing to do with the electric dipole. So, which is this polarization. So you should not confuse these same words for different phenomena. So by contribution of those medium, by polarization and current and magnetization, you have this complete Maxwell's equation for the medium. Okay. Instead of a simple E and B, now you get the E, D, H, B. Okay. So this is the medium. And for the case of electromagnetic wave components for the in the vacuum, so we are going to think about rho equal to 0 and z equal to 0. And as you know, I'm not going to give a detailed one, but if you make one more call and one more call, and then this call B will be goes to this one, so that you get the second derivative in time. Call will give you this relationship, and then by using divergence equal E equal to 0 over here, then this term goes away, and then you get this Laplacian goes here. Okay, so that basically, as you see here in the case of a vacuum, the electromagnetic wave or light in a vacuum satisfy these equations: wave equations for electric field and wave equation for the B. Those wave equations are identical. That's the reason why we get initially very similar form for the electric field and magnetic field in the case of a planar wave. And now it's time to think about the index of refractions. And if we have a certain medium, which is not a vacuum like this, but we are still assuming that there is no free charge, no free current, and then the velocity is changing by this medium, which is changing from epsilon 0 over vacuum to epsilon, mu 0 in a vacuum to mu. And then our velocity of the light in the vacuum is going to change to v. And the ratio between these two are actually refractive index n. Okay. So in most of the cases, when we are dealing with the light optics, we are going to assume that it is a non-magnetic. That means only the polarization will kick in, and then there is no sigma, no magnetization. So that only the dipole moment of the medium will change the refractive index. Okay. So refractive index can be actually imaginary number, and then that means the real part and the imaginary part will contribute to this one. So imaginary part will have a damping, and the real part will be the propagation part. Okay, so real part will contribute to real propagation in the medium, and imaginary part will give you the damping or attenuation of the amplitude. Okay, we are going to think about many dielectric medium like all of these. Okay, fused quartz or silicate flint glass, and depending upon refractive index, we have a very different response. Okay, so for instance, white light comes in and then the angle of the refraction will change as a function of the refractive index. Okay, so fluorite has a very low refractive index, which is below 1.45, but silicate flint glass has a very high refractive index, over 1.6. Okay, and now it's time to think about energy and momentum of light wave. And with a certain vector calculus, you end up with these equations. Divergence times E cross H is roundable on T, half over epsilon E square plus half over mu H square minus sigma E square. And the integral form, you get the volume integral over divergence is changing into surface integral. Okay, so that you have this surface integral is change of time over volume integral. So that this is the electromagnetic field energy, and this is ohmic loss, and this is your Poynting vector, and energy momentum. This is the energy of the light, and this is the momentum of light, and this is the Joule loss. Okay, and we call it as a Poynting theorem. If you define the S is equals H and the Poynting vector, and then this is the Poynting theorem. Okay, so here is the electric field energy density and magnetic field energy density, and this is the ohmic power density, like this, and then this is energy conservations. And in the case of irradiance, what we measure here for the light is in fact the irradiance. So we have a time averaged Poynting vector, and then you can see here is the correlations. I is given by E square, B square. Okay, so you need to remember that intensity or irradiance is related with the E square over B square. Okay, so that's the thing we are going to utilize it in the next classes. Okay, thank you. So we have reviewed the very basics of the wave motions. X plus minus Vt is the key note, and then we review the Maxwell's equations, and then we come up with the wave equations, and then we thought about electromagnetic wave, how the electric field and magnetic fields are satisfying actually the Maxwell's equation and the wave equations. And then we have considered two cases, harmonic waves. One is the planar harmonic wave, and the other one is the spherical harmonic wave. And then we have defined the Poynting theorem, which correlates the momentum of the light and the momentum, the energy of a light is how they are correlated to conserve the energy of the light. Okay. Thank you very much.